Hello everyone. This is our second lecture on transformer neural networks. If you remember, last time we started to look at the encoder only, or just encoder neural networks, where you have a structure like this. For each token of a sentence, your network learns queries, keys, and values, and using them, it calculates what we call attention, which is how much each token associates with other tokens. And before that, you have to project these tokens into a higher dimensional space using an embedding matrix. And we'll learn about that as well, the meaning of it. We learned that this is the meaning of individual words, and then to learn the meaning of a word in a context, like the word bank in I deposit my money in the bank, or we visited the river bank. That is the rest of the words that tell you which meaning the bank has. That is captured by these attentions, which is association of each word to the rest of the words or tokens in the sequence. And basically, one thing that we stopped right at the end of last video was you don't have one single attention or attention head. You have several of them in a transformer. Okay, and I mentioned it several times. I said there are like 8 of them, and so the dimension of the higher dimensional space, D of the model, you are going to divide it by the number of these heads, and that is the dimension for the QIs, KIs, and VIs for each one of those for each token. Okay, so now the question is, and the same with this H, the representation that you have, the contextual representation, is also of dimension dk. So the question is, why do you need several separate attentions and train them? Why? This is the explanation. Let's look at the sentence. The bank approved the loan even though the client had debts. So even though the client has debts, the bank approved the loan, right? This is your sentence. Okay. So the model here needs to understand not just one single relation between these words, a bunch of different ones. Like what? Like, for instance, bank is the one that approved the loan. So if the sentence, if the neural network needs to learn from this that who approved the loan, what was the subject of the sentence, it was the bank. Then the bank has also a relation with the loan. Hey, what was it that the bank approved? What was the product of this institution bank? It was the loan. What about the loan itself? Loan has what relation to which token? Well, for instance, it's related to client. You want to know who got this product, who got the loan, and the answer is the client. Yeah? And then you want to know why the client got a loan, because he had debts. So you need to basically look at the financial state of the client. And here, this even though basically demonstrate that contrast, that the guy has a loan, still the bank approved the loan. Yeah? So yeah, the reason was debt, but also because he was under debt, probably not a great credit score or anything like that, or ability to pay a lot of it, still the bank approved the loan. So these are all of the things that this single sentence has in it. And your neural network has to understand each and every one of it. It probably also needs to learn from the previous ones that had means it was in the past. Approve means it was in the past. It's not something that happened like right now or will happen in the future. It happened in the past. You have to learn all of that. So to do that, you cannot do it with one attention head. You need to have several attention heads simultaneously, that each one of them captures one category of relations. For instance, one of them learns the semantics, one of them learns the syntax, one of them learns the discourse, and so on. So all of them together hopefully can capture everything that you need to know from the sentence. Okay, so one single head is not clearly capable of getting all of them, right? So when you have a multi-attention head, for instance, head 1 can learn syntax. You can call it syntax head. So what does it do? It looks at the grammatical relations, right? Yeah. So it knows that, first of all, approved was in the past. As I said, had was in the past. And then approved is the verb that is related to the subject bank, and the loan is the object of the sentence. So it tries to learn these things. So if I give that sentence to ChatGPT and say, hey, what is the object of this sentence? What is the subject? What is the main verb? It is able to find all of them. Well, probably it can catch it with one of these heads. The second head talks about, for instance, the entity and the role. Like tracks, roles, and entities. Like what? Like for client, it knows that client has big attention to the loan and debt. Okay, so client had a debt, he had to get a loan for that or for something else. And this is basically show you the context of the financial situation or context. The other one could go about the discourse head. Like what? Like connectors. It looks at the connectors. The one you have here is even though, so it knows there is a contradiction here going on. If there is a but, and, all of those words that we know, so and so forth, it knows that, well, they mean the same thing, they mean different things. One is the conclusion of the other one, so it can look at the discourse. How you go from one sentence to the other, how these two sentences are related. Okay? And finally, you can have a position head. So it can encode most of the positional and structural info. Remember, I told you it's not just enough to encode each word, the meaning of it, and the contextual meaning of it. You also need to know where each word is inside the sequence, and that is called positional encoding. Now, I'm going to tell you in a second what positional encoding is, but one of the heads can mostly capture that one. Okay, so because you can look at one single sentence from so many different angles, ideally one or two or several of them needs to be captured by one or two or several heads. Okay, yeah, one head is not going to do that. So now you have H heads, right? Each head, for each token, it has generated these queries, keys, and values using these projection matrices W, Q, WK, and WV, right? Okay, fine. And so using the all of these W, Q, K, and VIs, which is for each token, right? You're going to pass them, and you can get what? You can get, this is the attention layer for head number I. So you have H of these heads. And let's say your sequence has n tokens in it, right? The total dimension of the higher dimensional space is D model. The dimension for each head is dk, which is D model over H. Good. So each head will learn these WQs, WKs, and WVs for the query, key, and values. And then you can get the individual Q matrix, K, and V matrix for each head, which are going to have dimensions of n by dk. Why n? Because you have n of the tokens, and each one has a dimension dk. And then you can perform the Q K transpose over square root D to get this similarity score matrix, and then pass that similarity score matrix to the softmax function to get your attention weights. And finally, multiply the attention weight matrix by the vector of values, and that will be the contextual representation for the all of the token sequences that are captured by head number I. Good. So this H is, as I said, the contextual representation for all of the tokens captured by head I. Now that you have several of these heads, you have head 1, head 2, all the way to head H, the way that you get the total H of all of these basically heads, The way you do it is by concatenation. Okay, so you are going to concatenate the whole thing. And since each h had a dimension of n by dv, now you have h of them, your dimension will be n by h times dv, which is d model. So ultimately, this concatenated h of all of these heads, the dimension of it will be n by d model, the same as the embedding matrix. And finally, what you do is you basically multiply this h by a linear basically layer, right? So when you concatenate all of this, then you multiply it by a simple fully connected layer where all of the weights and biases are included into this matrix WO, which has dimension RD model by RD model. And this is going to be what? This is going to be the output of all of these H heads, right? Good. Now, is that the final output of the encoder transformer? No, there is more to it. This is just the multi-head part so far. Now, before we go to see the rest of it, which is n stacks of these multi-heads side by side, along with the norm layers and the we have two things here, right? So we have the norm layer as well as the so this is one layer normalization, and the next thing we have is a basically feed forward network again at the end of it. So at the very end of it, this is what you're gonna get. This is the multi-attention head. These are the add and norm, and then each one, the output will go to a feed forward, another add and norm, and then the final output is gonna be n stacks of these multi-heads. So the structure of a encoder transformer has way too many things in it. So far, all we have covered is coming here and here. These are the two things I have covered, multi-head and input embedding. Now I want to talk about this positional embedding, which needs to be combined with the input embedding before sending it to the attention heads. And then I need to talk about this add norm and the feed forward. So finally, we can have everything that there is about a encoder neural network. So let's go back and look at the rest of the detail. As I said, one of the things you need to have is positional encoding. The way that an attention system works, you lose the spatial connections, the spatial positions. So you know there was a word called car or motion or any of these that you have, but you don't know where that word was. What did it come in the beginning of the sentence, middle, end, what? Because those will have effects on the meaning of the word. So we need to encode that position as well. Now, how do we do it? Well, so this is this part that I explained. There is no inherent notion of order. So, first of all, the thing that you send to the attention layers, as I said, is the one coming from the tokens and the position embedding, and then you send it to attention. So this X that you see here that we said we're going to send to get the Q's and the V's and everything, this here, this X, is not just the ith row of the embedding matrix. It is the ith row of the embedding matrix plus the basically position embedding for the ith token. Okay, so this X from the embedding matrix plus some data from the position encoding, that is what I will send to a multi-head. And you can see that right here as well, as I explained to you. Here. You combine these, then send it to multi-attention. So let's talk a little bit about this position encoding. How do you exactly do that? Okay, as you can see, I made a big document for you to explain as much as I could about transformers, so it's like 32 pages, and we're going to break it into 5 videos. So, how do you do that? Well, the original transformers, they used a fixed positional encoding. Using what? Using sinusoidal, basically, functions. They use sine functions and cosine functions, and they encode the position of each token. The new ones, they learn it. The modern versions of the encoders, they try to also learn the higher dimensional vector. It should also be in the D model space, right? Because remember, X that comes out of the embedding is a D model by 1. So this positional one should also be a D model by 1, so we can add them together. So they try to learn a separate higher dimensional in this space for the positional, okay? And they try to learn that. But original ones, they try to have some fixed function, so they reduce the number of parameters to be learned. So how does it do that? Well, this is the answer. Let's say you have one token in a sequence and the position of that is shown by variable POS. Okay? And the dimension of the model is all the way to D model, as I said. So the ith index, the ith direction in that higher dimensional space, we can show it with I, where this I changes from 0 all the way to D model minus 1 in a 0-based system or index. So remember, you have to take a pose, which is a scalar. It's just one number. It's position 1, position 2, position 3, or you can say position 0 if you're looking at Python, right? And you have to take this scalar and take it to this higher dimensional space. So each token has the scalar position, and in this higher dimensional space, these D model directions that you have, the ith direction of that, you're gonna show it with index I. So far, so good. Now, what do we do here? The functions that they used for positional encoding, as I said, is a combination of sine and cosine. So they use 2 functions to make it happen. What are they? The first one is sine, the second one is a cosine. The sine is used for the directions in the embedded space that are even directions. So index 0, index 2, index 4, all the way to whatever index it is. And for the odd indices in that space, we use what? We use a cosine function. So again, for 0, 2, 4, 6, these are all going to be sines. And then for 1, 3, 5, 7, we are going to what? Use cosine. Now, let's look inside this sine and cosine function, see how they look like. Inside of them, what do you have? You have position divided by a big number. What is the big number? The big number is 10,000 to the power 2i divided by D model. So basically this guy here, this 2i divided by D model, that's just a number between 0 to 1 because I is, or actually between 0 to 2 because I can at most be D model minus 1. So this is going to be bigger than 0 and a little bit less than 2. So this is all it has. Therefore, 10,000 to the power of that is going to be anywhere from 1 to what? To 10,000 squared, which is 100 million. Okay? This is, again, this is the kind of function that was used in original encoder transformers like BERT and so on. BERT used this one, the model BERT. So here you see that I'm dealing with what? With pose divided by a number that could be anywhere from 0 to 100 million or 10 to the 8. Why 10 to the 8? We'll see. But what is it that you have here inside the sine or cosine? So, you know, for a sine or cosine, this guy here determines the frequency, correct? As well as this whole thing. So is it, especially this one, not that one, sorry, this one, this denominator, this 10,000 to the thing. This determines frequency, right? Because you can also write it as sine of pose times 1 over 10,000 to the 2i. So if pose is your input, the frequency of the sine or cosine is determined by this number, 1 over 10,000 to the something. Good? That's the frequency of the sine and cosine. So, as I goes from 0 to d model, initially this number, this is 1, sorry, this is not 0, this is 1. It's some number to the 0, which is 1. So for small i's, your frequency is about 1 over 1, which is low frequency, which is high frequency. And as I gets bigger, when I gets bigger, your frequency drops. So the initial ones, they have what? The initial ones, they have high frequency. And as you go up in the indices, your frequencies is going to go down. And that's what I showed here for you. So their position values are some sine or cosine of position times some frequency, which depends on the index I. Okay, now what's the meaning of this? What does this actually do? Well, let's take a look here. So, as I said, this frequency is changing, right? It's getting from big numbers to small numbers. So I can say that for one I, if I call for I equal 0, I can call the frequency, which is 1, let's call it omega naught. And then for I of 1, let's call it omega 1. And then for I of 2, let's call it omega 2, and so on and so forth. Your positions, which comes from these two values, is basically a bunch of pairs of what? Sine of some frequency times pose, like omega naught times pose, and the complement pair cosine of omega naught times pose. So this is for the first I, the first frequency. Then for the second I, you're going to get sine of omega 1 pose and cosine of omega 1 pose. Another pair, a little bit less frequency. And then sine of omega 2 pose, cosine omega 2 pose, and so on and so forth. Yeah? Good? Until the very last frequency. Now, what is this? What do you think we are doing here? Does this combination of sines and cosines with different varying frequencies, does it remind you of anything? Yes, you are. This is a similar notion to the Fourier series. Remember, in Fourier series, we try to basically approximate a function with a combinations of sine and cosine with different frequencies, varying frequencies. That's the exact same thing you're doing here. With these pairs of varying frequencies of sine and cosine, guess what? You are going to basically approximate or embed the position for any token that has in position pose. Now, of course, when you change pose, all of these numbers are going to change, right? So you get a different set of weights for these sines and cosines. And if you change another pose, again, you're going to get another sets of sine and cosine. Now, you might say, well, great, this is kind of similar to Fourier series. Why do we have high and low frequencies? In Fourier series, I kind of get what you need, high and low frequencies. You want to change the fast variation and the slow variations of a signal. What about here? Is that something similar? Yes. So, small I, which means high frequencies, they are good when the value, which is the information of the tokens, changes a lot as you go from one position to the one next to it. So if I have one word here and one word next to it, and these two have quite a bit different meanings or context, this sudden or fast change can be captured by high frequencies, which are small i's. So the ones with the small indices, the directions in the high dimensional space with small i's, they can capture these fast changes between the meanings of the words. But if I is large and frequency is low, this is when the meaning is barely changing. You go from here to here, but the meaning of these two words are very close. Okay? Yeah? So high frequencies are good to capture local order or small differences in positions. Low frequencies are good for capturing rough locations, which are like beginning or middle versus like the end. So this one kind of more gives you that you move from 3 to 4 or 4 to 5. These ones will kind of give you an overall, hey, your word is somewhere in the middle. Not exactly where, but in the middle. This one can tell you a little bit more. So you see, we are not directly do a one-hot encoding or anything. We are doing this as a function approximation. And this is how you do the position embedding. Great, fine. Let's move on. Now that we have the position embedded as well as the token embedded, we're going to add them together, as I said, and now we're going to send it to all of these heads. Now, once you calculate these heads, what are you going to do to the output? As I said, you need to look at the add and norm. So let's look at this region here a little bit and explain that. Let's go back. So after combining the attention heads and the projection WO, which I just explained to you, right? It's this guy here. This basically projection that you have. Once you do that and you add your positional embedding, right? So you pass it to multi-head attention layers. The output of this multi-head attention, which you can see here, this one is, we're going to call it the multi-head attention of X, where X is the sequence of all tokens, input of the system, and output is MAH of X. Good. So you get the MAH of X, and now here you do something very interesting. Instead of directly sending the MAH of X to a layer normalization, you do something interesting, which is called add. Remember here in these pictures, I always showed you add and norm layer, right? You see here, it says add and norm. So what is this add part? This is the part that we want to explain. Add means you add the input of the MAH to the output of it, then pass the result to the layer norm. Okay, so if I go back here, this input X that you send to the multi-head and the output of it, MAH of X, you add these two guys together, then send it to a layer norm. Why would you want to add the output and the input instead of just the output and then take a layer normalization? What's the point of this adding of the input to the output? Well, let's explain that. So we can say that add layer, or residual in this case, is what you add the inputs and the outputs. Okay, what's the point of that? This idea, this rationale of adding input to the output came actually from the residual networks, ResNets. Why? What's so good about adding it? This is the good part. Remember, in back propagation, you always need to take partials of outputs of any layer with respect to input of the layer. So we need to calculate this kind of matrix, right? Fine. If I take a partial with respect to x of this formula, what would you get? You get partial of output with respect to x is partial of x with respect to x, which is identity, plus partial of the multi-attention head. So if you call it f, this multi-attention head, this is the derivative of that. Now what's good about it? This is the good part. Sometimes the output of that multi-attention head f, or MHA of x, barely changes as you change your input tokens or sequence. Okay, in other words, this partial derivative, this whole thing here, is something small. And you know, if this is a small and this term does not exist, this input does not exist, then this partial that you need in backpropagation is going to be a small gradient. And you know, a small gradient always means slow or stalling in backpropagation and convergence of the parameters. So here, by adding the input, you're adding a 1 to the gradient. In other words, you're forcing your gradient that you need to at least have a magnitude like 1, even if this portion of multi-head does not produce much of a gradient. So this definitely helps with the gradient vanishing problems and with the optimization. Okay? So if f prime is, which is this guy, if this is small or sometimes noisy, this identity part help it not be a small gradient and be a little bit more stable by adding a big number to the noise. Okay, so it's really an optimization thing that you are doing. If you want to explain it in very plain English, this is how you do it. You said by adding this input to the output, each one of these layers that is adding them together, this add layer, is not going to completely replace the input by the output, right? So it's not just going to get the input and replace it by output. It's going to replace the input to input plus output. What does that mean physically? The meaning is actually this multi-head is not going to completely overwrite those embedded X's and forget whatever they were. Actually, it's going to refine it. This part here is the refinement to those individual meanings. Because remember, this X is what? This X. This is position embedding and individual token embedding. This one is the context within the sequence embedding. So instead of I replace our individuals and positions with only within the sequence, I keep them and I add that to it so I have everything and not forget anything. Okay, so that's saying it in plain English. Now finally, we have to send it to a layer normalization. Why do we normalize, right? You probably, if you look at my earlier videos, you know why we do layer normalization. But why do we do it? How do we do it? So let me explain both. The way you normalize each token feature vector, this x plus MH of x. You subtract for each token, you subtract it from the average divided by the standard deviation. That is going from average of mu and standard deviation sigma to average 0 and standard deviation 1, which is what we call normalization. So mu is the mean of components for token x, and sigma is the standard deviation of components for x. So you bring it down to a distribution of average 0, standard deviation 1. And sometimes it's not good to leave it at 0 and 1. Sometimes it's a good idea to scale it to, instead of 0 and instead of being from average of 0, you want to shift the average to beta, and instead of standard deviation 1, you want to shift the standard deviation to gamma. So sometimes you want to linearly scale it up from mu and sigma to beta and gamma. where beta and gamma are the things that you're going to learn. Mu and sigma you calculate directly, but beta and gamma are the one that you try to learn to scale and shift. This beta is shift, gamma is a scale, because that distribution works better for your network as opposed to just mu and sigma. So you normalize it and then linear is shift and scale it. And again, you learn these guys. So these are some extra parameters. Okay? Now, if you don't do this, what's going to happen? Then all of those output that comes from the activation function, they can grow very large, they can drift, they can shrink, they can explode. In other words, mu and sigma can be, especially sigma, can be very large, very small, and that mu can, instead of 0, can shift significantly to the left and right. So by this normalization, you always forcing it to stay in this range as opposed to these guys that are constantly changing, going up and down. You kind of force it to always stay what? Within the same range. So later, actually, let me show you. Later, when all of these different stacks come in, right? Because now you're sending this output to a linear, add norm and send it out. You want to make sure the scale of the parameters coming out of this first stack of multi-head to the second stack, to the third, to the nth are kind of similar scale. Otherwise, one of them will dominate the rest of them. So you want to keep them all within the same range so none is dominating the rest. That is the reason for normalization. Okay. Now, once you do that, you're going to pass it to a feed-forward network, FFN, which is basically a multi-layer perceptron, okay? This is a multi-layer perceptron. So you're going to get the output of the norm layer multiplied by a weight matrix W1, add a bias W2, then pass it to a nonlinear function sigma, which you pick, and then you can multiply it by another set of weights and another set of biases. And again, all of these weights and biases are matrices and vectors for you, or matrices to learn. You have to learn it. Okay? Yeah? So if the output of the norm layer, the first norm layer, is X, by passing it through a couple of fully connected network, and first in the middle by a nonlinear function, you get your feed-forward network. And then once you have the feed-forward network and the output of that feed-forward network, you can call it F. Then that F is again gonna go to another add and another norm, okay? So this F, which was the input here to this last one, is gonna be added to the output of it, which you call Z. So that's the adding part. Then take a layer norm and finally get X output. Now we know this add and norm, why we do it. So we don't forget previous things and we keep them from exploding or shrinking. But what is the role of this feed-forward? Why do we need this feed-forward? So looking at the dimension of these weight matrices, W and B, can tell you something. If you look in the first part that we multiplied the input X by W1 and B1, the dimensions of these guys are demodeled by a new dimension called DF and DF and just DF. And once you pass it through the nonlinear activation function sigma, the output of that is multiplied by W2, which goes from DF to demodel and demodel. So what does that mean? Means you go from a dimension demodel in X to DF in the output of sigma, and then by multiplying it by W2 and B2, you go back to model to the dimension demodel. Now the question is, what is this DF, the dimension of the feed-forward network, this hidden hyperparameter? What do you pick for it and why you make it different than demodel? First of all, in many transformers, they pick something like 4 times bigger. So you go from a dimension demodel to a dimension bigger than that, DF, and then go back to demodel. So you go something like this, right? Here the dimension is D model, the input X. Here is the sigma of W or X times W1 plus B1. The dimension is DFF, which is like 4 times bigger. And finally here, the output of the FFN of X, you are going to go back to D model again. This is what we call a wide bottleneck, because bottleneck is like this. You go from big to small to big. This is the opposite. In the middle, instead of being narrow, it's wide. So we call it a wide bottleneck multi-layer perceptron, or MLP. Why would you do that? Why would you expand and then shrink back? Well, the reason is this. When you momentarily expand into a higher dimension, like 4 times bigger dimension, you are allowing your network to capture and represent even more complex contexts and notions that your D model could not easily capture. And then by passing it through a nonlinear function, you're allowing it to even capture more transformations. Because if you don't use the sigma, then you can combine W1, B1, W2, B2 into a single W and B, right? And that basically does not do 2 things, it's just 1. So adding nonlinearity and expansion, allowing you to capture more complex nonlinear transformational features. And once you capture them, now you're going to compress them back. This will allow the representational power of each layer to significantly increases. So this is another one of the innovations of the people who came up with it, this sudden expansion, nonlinear, and then going back. Okay, this is some of their amazing work, which happened to be working very good, as you can see in ChatGPT or other ones. Now, we said sigma is a nonlinear function. What kind of function would you use? One of them is the ReLU function, as you know, rectified linear unit, which is the max of any number n z. So basically, when z is negative, you're going to get 0, and when z is positive, it's just going to be the identity line, right? This is the ReLU function. If you don't know about it, go ahead and look at my original videos on deep learning, and you're going to see it in the videos that is about functions in deep learning. I talked about ReLU and why ReLU is a good function. Okay, there is another one that I have not talked about in those videos, and this is an interesting one. This is called the GELU function, Gaussian error linear unit. What kind of function is this? Here, for input x, the output is going to be x times phi of x. What is phi? Phi is the cumulative distribution function of a standard normal distribution. Okay? Yeah? You know, it doesn't have, because that is the integral of something like negative x squared over 2 sigma squared, right? dx. This does not have analytic integral. You just have lookup tables for it. Phi of x. Doesn't have a formal shape. But there are lookup tables for each value of x. There are equivalent values for that. Okay? So many cases, instead of these transformers do the table lookup, they use an approximation for this, because there is no analytic closed form solution for that. But you can approximate it by this 1 plus tangent hyperbolic of this cubic polynomial times a linear function. So this can be approximated by this. And many times they use this one. Okay? Now, what's so nice about this function? This function is a smooth function and probabilistic. Probabilistic because it is related to a normal distribution. Smooth means what? Well, here, if you look at this origin, this is where this ReLU function does not have a derivative. And derivative is what you need in backpropagation. At this point, derivative is not defined. You have a broken corner. But if you look at the GELU function, so ReLU here is the dashed red line, GELU is the blue one. Look at that. At big positive x's and big negative x's, it converges to the ReLU, but at the origin, you have a smooth curve here. Okay, so that allows you to take partial derivative of this GELU of x with respect to x without any difficulty, especially when you use this approximation, not the lookup table, because lookup table does not give you a function to take derivative from. So you use that, you easily take a derivative from that, and it helps with the backpropagation. So many times they use the GELU function. I just wanted to talk about it since I have not talked about it. And finally, as I said, you combine the F and Z, right? Where the Z is the output of the feedforward. F is the output of it. Z is the output of, F is the input to the feedforward. Z is the output of the feedforward. You add them together in the add and then take a layer norm, and finally that's your X output, as I said. Now you can see the entire structure of a encoder only transformer. You see, so even a simple encoder transformer has a very, very complex structure. But hopefully from previous video and this video, you understand what kind of detail it has and why. Now, before we end this video, we're going to look at one interesting thing. Remember, we said that these transformers, they have tons of parameters that they need to learn. For instance, the original BERT network that I mentioned to you, the original BERT encoder, which is just an encoder transformer, this guy had about 110 million parameters. Really? I mean, how much data does it have? How many parameters? How do you end up with 110 million? Well, let's take a look. So, if you look at the BERT, the original one, the dimension of the higher dimensional space that you had was 768, as opposed to ChatGPT, which is 2900. It was about a fourth of that. So much a smaller space. And the number of vocabulary that it has was only 30,000. Remember, for ChatGPT, this is 201,000, 7 times bigger, or 7 times bigger. The DFF was 4 times D model, as you can see. Okay. For max position, the dimension of the max position was 512. It has 12 stacks of encoder layers. So each one of them with a multi-attention head is 1 stack. It has 12 of those. And then there are 2 IDs for each token. What is that? I'll tell you. But this is the detail for the BERT standard, the one that was originally introduced. Now, how would you end up with 110 million? Well, let me tell you. First of all, it could handle pairs of sentences in one input. What does it mean? It means if you have a clear screen and then sentence A and then a separation, a space, and then sentence B and again separated, the model will allow you to basically know that which token belongs to which sentence. So if you have one token in sentence A and sentence B, the same token, you should encode that this is from sentence A or sentence B. It allowed you to do that. Right now, you don't have to. You can consider the whole thing, sentence A, B, all of it as a single sequence, but it allowed you to do that. So you had 2 IDs for each segment. Like ID 0 was in sentence A, ID 1 was in sentence B. That is what this 2 is all about. 2 segment IDs. Good. What else? The other thing it had, it was called maximum sequence length. So you could not give that BERT a sequence that was, I don't know, 10,000 words or tokens in it. You had a maximum position or size really for your sequence. Okay? So when you did your position embedding, it would only be belonging to the space of max position by D model. So as long as your position was 0, 1, 2, all the way to max position -1, no worries. You could learn it or you could use those sines and cosines. Okay? But if you wanted to go beyond max position, like, hey, your sequence cannot have more than 500 tokens, then it will not give you any position embedding for those extra positions. So you could not encode their positions. Okay? So you better keep it within that limit. So that's another parameter that you had, and that was 512. Okay? So you could only go to 512 positions for being encoded, no more. Now, how do you end up with the 110 million? Well, remember the first thing you had was the embedding matrix. Dimension of that was vocabulary size by D model. Well, that's your vocabulary size for BERT. This is D model. Multiply them. Here you are looking at what? 23 million parameters. So just embedding the original sequence of tokens for that would take 23 million parameters in that matrix. What about position? Well, you only allowed for 512 positions, and each one will be projected into the high dimensional space with D model. So to embed that, the matrix for embedding will have about 400,000 parameters. Then what? Then you had two segments, segment A and segment B. Remember, sentence A said sentence B. Each one of them will go also to the dimension of 768. So 1500 just to do that. It's not really a big part. The big parts are the other ones. This is something that is very small. Then you have a layer norm. If you remember, layer norm has what? A layer norm has a bunch of gammas and betas that it needs to learn. And each one of them has the dimension D model. So that's another 1500. Again, not a big thing, but you should count it. So just the embedding part, before you even send it to the attention one, you're looking at 23.8 million parameters, which most of it comes from individual tokens and a little bit of that from position. Okay? This is before you send it to the attention heads. Now look at one encoder layer which has a multi-attention head in it. Remember, each attention head has WQ matrix, WK, and WV. Their dimensions were D model by D model. Okay? And you had this WO, the final one, which has similar dimension. So here you're looking at about 600,000 weights for these matrices. Okay? And basically, since each one of these matrices was about 600 and you have 4 of them, you're looking at 2.3, 2.4 million for the total of all of these W matrices. You also have 4 biases. Okay, 1 bias for each one. And that is another 3,000, which is not a big deal. Again, about 2.3, 2.4 for attention parameter per layer. Then remember, we had a feed-forward network, which has W1, W2, B1, and B2. And with the dimensions of D model and DFF, and with those dimensions I showed you for W1, 2, B1, and B2, W1 and W2 have the same dimensions. Some of them is about 4.7 million. B1 and B2 just small, like 3,000. So the whole feed-forward network will have about 4.7 million parameters. Okay? So if you add everything together in one encoder layer that has a multi-head attention, and or one multi-head attention, and then feed forward, and then the ln, right? You are looking at 7 million total parameters. Okay, you have what? 7 million parameters per one encoder layer. But remember, you have n of them, a stack of n of them. And here you have 12 in BERT. So 12 times 7 million, that's 85. Added to the original 23 that you have for embedding, you're looking at 108, 109 million parameters. Okay? So 110 is not a big deal, even for something as simple as this. The vocabulary size is limited, the D model is small, it has this extra ID thing, but that's not a big deal, right? And basically, you see that here we are really dealing with this. So H is not given here, so we don't know how many H's. Let's see. No, it doesn't say H, but so these dimensions that you see here, these are the ones for the concatenate multi-head. It's not just for individual one, because remember, each individual one was D model by dk, and this dk was D model divided by H, each individual head. But when you concatenate them together, ultimately it will be D model by D model for all of these W's, which is what you can see. So we don't even need to know the H in this case, because this is like the concatenated one. Okay, now if you're wondering, well, if you have 110 million parameters, so that the transformer does not overfit and doesn't just simply memorize everything, which means allocating some parameter for each one of them, how would you make sure it doesn't overfit? Well, to do that, you have to give it a lot more data than these parameters so it can generalize. So how much data was used to train the BERT? Well, if you look at it, the original paper said there were two sources, or we call corpora, for training. Okay? Yeah, and corpora is the plural form of corpus. What is corpus? Corpus is a data set that can come from many different types of documents. So there were books used to train it, articles, and web pages. Of course, it was not multimedia format. It was just text. It was not any picture or anything like ChatGPT. It was just text, but it came from books, articles, web pages, and so on. And so if you look at it, the ones that came from books, they had about 800 million words of text in them, and some books that were not even published. And they also used the English Wikipedia, which has 2.5 billion words. So how many words or token have used to train it? 3.3 billion, as opposed to 110 million parameters. You see, look how many times your data should be bigger than that, so you don't overfit, so you don't memorize. Now imagine for ChatGPT with 5 trillion parameters, how much data is used. Then you might say, what kind of cost function did you use to optimize it? Because when you train it, you have to minimize some cost function. You have to give it some data with some kind of labels, kind of supervised learning, and try to minimize a cost function so these weights converge to something. What kind of cost function was used? Well, it was trained indirectly with two different prediction tasks. The first one that was given to it was called masked language modeling, or MLM. The second one was called next sentence prediction, or NSP. What does that mean? In MLM, you try to predict masked tokens. So if I give you a sequence of tokens, right, and then next I give you the same sequence but with one token randomly selected and delete it from the sequence and say, hey, which token should go there? Right? Since I randomly selected it myself and I know which one was it, I have the training data. The training data is the missing token. So if the network could exactly predict the missing one, great. Your weights are such that your cost function goes down. Otherwise, guess what? You have to change it. And the same thing with binary classification for sentence pairs. Okay? Well, what does that mean? So if I give you two pieces of text, A and B, and then ask, hey, is B really the sentence that should come right after A in the original document? Then you have two answers. You either say yes, B is next of A. So you say is next for A, B, yes, or no, not next, no. Okay, and again, since you have one sequence and then another, and you know the order of them, and whether it should come from that or not, you can again easily get the training data. Now, what kind of cost function was used? Because you are comparing something against something, the answer was cross entropy loss function. Okay, when you are looking at a distribution of answers for a missing token and the actual ones, and you want to compare these two, cross entropy loss function is the best cost function to use, and this is what it was used. Okay, and the way that they did this SNP, the NSP, I guess, next sentence basically prediction, half of the time they did it such that B actually naturally comes from A, half of the time they did it such that it's not, but it was actually random. Okay, so they took a random B from somewhere else in the corpus for some given A, and clearly that was not right after A, but half of the time they actually took exactly the next sentence after the input A and call it B and allowed the system to train. And as I said, for missing token, again, it was a random token that was missed, and it has to predict it. So it has something like this, for instance, for next sentence. I give you A and say, hey, he put on his shoes and grabbed his keys. Now I give you B. Then he walked out of the door to go to work. And then say, is B naturally come after A? If you say yes, that means you did the job right. But if A is, she opened the window to let in some fresh air, and then B is some random thing like stock prices rose sharply in early trading. If you say no to me, again, you did a good job. If you say yes, that means you didn't do it correctly. Okay, so BERT was trained with cross entropy on predicting the next sentence and predicting masked or missing tokens on 3.3 billion words from English Wikipedia and a lot of books and so on. So hopefully at this point you know enough about encoder transformers, and in the next video we're going to start talking about the decoder transformers. So we're going to look at encoder decoder transformers, like the one used for translation, continuing the rest of a sentence and so on, like ChatGPTs. So we're going to look at that, and we briefly going to look at vision transformers, VITs. Okay, so thank you so much for your attention. I'll see you in the next video.